Today in math class we're looking at lesson 38, which is all about simplifying expression using the GCF, also known as the greatest common factor. What a video that goes through each of the different example problems. Example 1 about finding prime factorization, example 2 determining the GCF, example 3 factoring a polynomial, and example 4 simplifying algebraic expressions. Because I'm going to go through those right now and kind of teach as I go. So if you've watched that video prior to watching this one, you'll know what Mr. Shane's talking about as he goes through the practice problems, which are at the last portion of today's lesson. The lesson practices A through H. Let's take on these 8 problems to review what we've already learned because we've watched that video and gone through those previous examples. In the first one, letters A and B are from example 1, finding prime factorization, in which you're thinking about prime numbers and how the smallest prime number could be multiplied by something to break a number down. Here you've got 100. What I like to do is to set up this tree, and I say, well, what can I divide that number by? If it's even, it is always divisible by 2, so I'll say 2 and what equals 100? 2 times 50. So those are 2 factors. We'll then take the next largest number that isn't a prime number and break that down so that they're all prime numbers. 50 can be broken down into 2 and 25. 25 can be broken down into not 2 because there's a 5 at the end of it, not 3, not 4 is not a prime number. How about 5? 5 and 5. So the prime factorization is 2 times 2 times 5 times 5. And this is what my answer looks like. Or it can be written with exponents to say 2 squared times 5 squared. Both of those would be acceptable ways to write a prime factorization of a whole number. Here you have an example of 51. Can 51 be broken down by any prime numbers? I start with 2 because it's not even. Obviously it's not 2. And then I go to the next set of prime numbers. So I have 2, 3. What multiplied by 3 would equal 51? In this case, it's 3 and 17. There's my prime factorization. Now, how do we take prime factorization of whole numbers and apply that to these really complex algebraic expressions? Well, to do so, we practice finding the greatest common factor. To find the greatest common factor of any number, we simply write it out as this huge line of all the factors that are being multiplied. So we're going to take 24 and use the prime factorization, and then we're going to write down m to the third as m times m times m, and n to the fourth as n times n times n times n. I should probably just show you. 24, let's break it down. 24 can be written as 2 and 12. 12 can be broken down into 2 and 6. 6 can be broken down into 2 and 3. Let's just double check our math. 2 times 2 is 4, times 2 is 8, times 3 is 24. Okay? Now I would write m times m times m, and n times n times n times n, and I've got that portion of my prime factorization done. Now I'm going to take the second term, 32m, n to the fifth, and p. Well, 32 can be broken down into 2 and 16, 2 and 8, 2 and 4, 2 and 2. So if I write that out, 2, 2, 2, 2 times 2 is 4, times 2 is 8, 8 times 4 is 32, or 2 other 2's, which looks like this. 2 times 2 times 2 times 2 times 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Now I'll write down my variables as factors, m, n, 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 because there's 5 of them, and 1p. Now to find the greatest common factor, once I have the prime factorization of that algebraic expression done, I circle all of the terms that are common in both of these. And I circle the number of terms that are common as well. And I want to find the lowest amount of each of those terms. So for example, I've got 2, 2, and 2, and 2, 2, and 2. So I've got 3 sets of 2's in each one. I have 1m in each one, and I have 5 n's here and 4 n's here. So I've got 4 n's that are in this one and 4 n's that are in this one that I could circle, that are the common terms or the common factors amongst those. If I take those and I write those out, that's my greatest common factor. So let's put that back together. The math on this would be, what's 2 times 2 times 2? Well, that's 8. M would be written as m, and then n would be written as n to the fourth. Again, write them out in prime factorization, everything multiplied by everything in its simplest term, and then I'm circling what is the same, or I'm finding the common factors in both terms and saying that's the greatest common factor. I can pull that out of the equation then, and that's what it gives me here. Let's try again in letter D. Here you have 5 p squared q to the fifth r squared minus 10 p q squared r squared. what I would do is factor this out first. So I have 5 times p times p. There are 5 q's. 1, 2, 3, 4, 5. R squared is 2 r's. And then I'm going to go to my second term. Here I've got 10, which I'm going to write out as 2 times 5. And I like to sometimes write them on top of each other like this so you can see what lines up and where those common factors align. You've got 1p. You've got 2 q's. So I put a little space in there just to show you that I'm kind of lining those up. And I've got 2 r's. Now I can identify where I have common terms. I've got 5. I've got p. I've got 2 q's. And I've got 2 r's. Now the greatest common factor between those is going to be where they have those similarities. So in this case, it would be 5 p q squared r squared as my final answer for the greatest common factor of those 2 terms. Now, where can I use that information? Well, in the next example, it tells me to factor a polynomial. Well, here I'm going to use the skill that I just learned to factor out a polynomial and then rewrite it as a simplified expression. So I use the same skill, the same thing I just did, and I just apply it in a little bit different way. Notice how it's a little bit different. Here in letters E and F, we're going to put these pieces back together to write out the simplified version with those polynomials that have been factored out. Here you've got 8d squared e to the third plus 12d cubed e squared. You're going to write that factored out. Prime factorization of 8 would be 2 times 2 times 2. D squared is d times d. E cubed is e times e times e. Right? 12d cubed e squared would look like this. 12 is 2 and 6. 6 is 2 and 3, so it's 2 times 2 times 3. You've got 3 d's and 2 e's. So there's both of those factored out. I find the greatest common factor amongst them by circling what is the same in each term. The greatest common factor that I find between those is 2 times 2, which is 4, d squared and e squared. So I'm going to write that over here. 4d squared e squared. But now that I've taken those things out, imagine it's like I'm actually erasing what's in both of those factors. Whatever I erase, whatever I factored out, I still have to think that there's other parts that are still in that portion of the expression. I can't just take those out and then the rest of it be gone. So whatever's left after I have erased those items becomes the factor, or what's being multiplied, what's left inside of the set of parentheses. So in this top portion, I have 2 and I have e that are left in that expression. In the bottom portion, I have these e's eliminated, these d's eliminated, and these 2's eliminated. I have 3 and d. So let's just remember that. In the top portion, I've got 2e. In the bottom portion, I've got 3d. Now here's where I would rewrite it based on what it looks like in the very first portion of the expression. Here I had the first factor of 8d squared e cubed. I would write outside of that 4d squared e squared. Inside of parentheses still is then what was in that portion. I had 2e in that portion. Now, here's a way to check to see if you got it right in the middle of the problem rather than waiting to the end. What if I did my distributive property and I multiplied right now? 4 times 2 would be 8. D squared would be d squared, and e squared times e would be e to the third. Would this multiplied together equal that? Well, then I've done it right. Then let's put together the second portion here. I again have 4d squared e squared. That's multiplied by the second factor. If it was multiplied by 3d, would it give me the same thing? 4 times 3 is 12. D squared times d would give me d to the third, and e squared's already there. I keep the same term that's here. That plus sign stays there, and then I put this second factor into my expression. So here's how I would factor out the greatest common factor. Once I found the greatest common factor, I'm just writing that outside and writing whatever was not factored out still inside of those parentheses. Okay? Let's try another one. Letter F says 12x to the fourth y squared z minus 42x to the third y cubed z squared. First I'll factor out. 12 is 2 times 6, and 6 would be 2 and 3. X, 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 y, y, z. 42 is an even number, so it would be written as 2 times 21. 21 can be 3 and 7, so 2 times 3 times 7. 3 times 7 is 21, times 2 is 42. And it would be x, 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 y, 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 z, z. The more you do this, the better you get at writing this out. You'll notice when I first started, I put each one of those little dots in between to symbolize that multiplication. Now I'm getting to the point where I'm working faster at this. I can just write those variables next to each other and know that that also means multiplication. Now I'm going to find the greatest common factor by circling what is common. I've got 1, 2 in each one of these. I've got 1, 3 in each one of these. I have 3 x's. I've got 2 y's. It looks like I have 1 z. Let's put all that back together. So 2 times 3 would give me 6. I've got 3 x's, which would be x cubed, 2 y's, which would be y squared, and 1 z. My GCF is 6x cubed y squared z. Now I take that out. Now whatever was not circled is going to stay in the first term and the second term. Now let's just remember where those are. I've got 2, and I've got x in this first term. In the second term, I've got 7, and I've got y, and I've got z in that second term. Write those back together. Again, in that first term, I had 2x. I keep the same sign here. And then I have z and y in that second term. Write the factor in front of it. And I have my factored polynomial. Okay? I took out what was the greatest common factor and then wrote it as this reverse order of the distributive property. It's kind of like doing the distributive property, but in reverse order. Distributive property, you've learned that you multiply what's on the outside by what's on the inside. Here we're reversing that whole process and going to factor these polynomials. The last portion is the factored expression, where it's not in this multiplication form or the reverse form of what looks like the distributive property, but it's when we've got a fraction bar involved. We know that when you've got something that's a like term in the numerator and the denominator, you can cancel those things. So if we can factor the numerator and denominator and find like terms, you can simplify the expression overall. Here you've got 6x plus 18 and you've got 6. What I like to do is to factor out the numerator and then the denominator, find where those like terms are, and then cut those out. So to write this out as a factor, you can go back to your prime factorization. 6x plus 18 would look like 2 times 3 times x plus 18. 18 is 2 and 9. 9 is 3 and 3. So it's 2 times 3 times 3. In the denominator then, I can write out the factor of 2 and 3. Now the greatest common factor between those would be what I can separate in the numerator and the denominator. In this case, I can take out the 2 and the 3 in both terms because I've got 2 and 3 in my denominator here, and I've got a 2 and 3 in the denominator in the top for both of those. So guess what? 6 is a factor that can be eliminated from both the numerator and the denominator for each of the first term and the second term. So if I'd write that out, 6 can go on the outside and be multiplied by what's still left. Here I would have x, and here I would have 3. That's just in the numerator, because if I would do the distributive property, again going backwards, 6 times x is 6x, and 6 times 3 is 18. I'd have that same answer, so here I've done this right. And then 2 and 3 would be eliminated and pulled out, turned into a 6 as well. But now I have my factor pull out of the numerator, and it seems to be the same as what my denominator is. What can I do with those two terms that are the same? I can cancel each other. Therefore, my simplified expression and my answer in this case is just x plus 3. Okay? The last one we have here is 18x plus 45x to the third over 9x. Again, we're going to prime factorize. Here I have 18, which is going to be 2 times 9, which is 2 times 3 times 3, and x plus 45x to the third. 45 is going to have 5 as its first factor, 5 and then 9. 5 times 9 is 45, so 5 times 3 times 3, and then x over 9x, which is 3, 3, and x. So the first thing I'm going to do is try and factorize the numerator. Separate the numerator from the denominator from the start. The prime factors that I have here are going to be 3, 3, and x, 3, 3, and x, and it just so happens that I have, guess what, 3, 3, and x in my denominator as well. But if I separate the numerator, in this example here, then I would rewrite this as 9x on the outside, because that's my greatest common factor. And on the inside then, I'm still going to have 2, and I would have, in this case, 5x squared. I put back together the denominator because it's 9x. I can't do anything with that. But then I now have the ability to cancel here, so that 2 plus 5x squared is my final answer. Now I know that was a lot of busyness going on the board here, but it's something that you could master by getting that prime factorization down as the foundational skill and then practicing it and practicing it and practicing it and practicing it. The more you practice this, the easier it's going to become. God's blessings.